So cognitive bias or judgment bias is often thought of as being a glass half full, half empty style of study. So let's say you have a glass and you can interpret it in an optimistic way, so thinking of it as being half full, or a pessimistic way and thinking of it as being half empty. Now we can adapt this style of study for work with animals by giving them a discrimination training where they have a reward paired with a stimulus as an S+, and another stimulus paired with the absence of reward. So one rewarded stimulus, one unrewarded stimulus. And then we can present them with an experience that will either put them in a positive mood and make them optimistic, or put them in a negative mood and make them pessimistic. And we can test whether or not their mood has changed by presenting them with an ambiguous, glass half full, half empty stimulus that sits between the rewarded S+ and the unrewarded S-. And what we can ask is, are you going to view this stimulus optimistically and assume it has a reward, or pessimistically and assume that it doesn't have a reward? Now, this type of study has been done in bumblebees before by Salvi et al. In 2016. What they did is take commercial bumblebees and allow them to enter an arena and engage in a discrimination. The discrimination was both a color and a position discrimination. So the bumblebees approached an array and they had a rewarded stimulus, in this example blue, on the left-hand side, and an unrewarded stimulus, or an S-, green, on the right-hand side. Once bumblebees were trained on that discrimination, what the authors did is give one group a surprise high-valued sugar water droplet that the bees would view as an unexpected reward to put them in an optimistic mood. And the authors wanted to know, how would putting this one group of bees in an optimistic mood change how they interpreted ambiguous stimuli? So they tested them on a set of probe trials that looked at ambiguous stimuli that sat between their S+ and S- stimulus. These are their data. These are latency data. So latency is going up the vertical axis here with longer times to approach the stimuli at the top and faster times to approach the stimuli at the bottom. And then their stimuli are represented across here with the ambiguous stimuli sitting in the middle. The control bees are in the solid lines, and then the bees that got that unexpected reward and should be optimistic are in the dashed lines. And what you can see if you look at this middle ambiguous stimuli is that those bees that are optimistic were faster to approach those ambiguous stimuli than the control bees. What that suggests is that they are optimistic about the possibility of getting a reward, so they're going to those stimuli more quickly. So here, it seems as though these authors have created an optimistic state of mind in these bumblebees. Now, in paradigms like this, or like the one I just presented, what you typically get is just what I showed you, a graph of response rate to the S+ stimulus, the S- stimulus, and then a set of ambiguous stimuli in between. Now we can imagine in this figure here that the black line are the control bees. This is their standard rate of response after training. And then you have a green line here when there's a positive manipulation, so putting the bees or animals in an optimistic mindset, and a red line indicating a negative manipulation, something that would put them in a pessimistic mindset. And that changes their response to the ambiguous stimuli. Now, authors often also include novel stimuli that are far removed from these stimuli to make sure that it's an optimistic or pessimistic bias that's changing behavior here and not just motivation. So if all bees respond similarly to novel stimuli, then their motivation is probably equally the same, and it's an optimism-pessimism thing that's changing responses over here. But there's a piece missing in what people are doing, and that's the other side of the generalization curve around the S+. When you train an animal on a rewarded stimulus, they create a full generalization curve in their response rate that goes to both sides of the S+ stimuli. So our question was, what is happening in this other half of the curve, this unexamined half, and can that give us more information on the mechanisms that are creating these ambiguous differences? So how we looked at this is we modeled it off of the Salvi et al. 2016 paradigm, and we did a color discrimination. But instead of just looking at an S plus and S minus, we added in a set of novel stimuli that capture that aspect of the generalization curve around the S plus that is not typically captured. So we have our S plus, our S minus, our ambiguous stimuli, and then two novel stimuli that sit quite close to the S plus. How we did this is we had a commercial colony of bumblebees. They were attached with a small tube to a large foraging arena. We trained them all on a color discrimination on a blue-green array, as shown here, to a criterion level of performance. We then took those bees and split them into two groups. One group got a high-valued, unexpected sugar droplet on their way into the foraging arena, and another group was held for a similar amount of time that it took those bees to consume that high-value reward. And then they were all tested on a probe array that had our full range of stimuli. This is a quick video of a bee doing that probe task. So this is the full range of stimuli, and we are recording their responses to all of these different color stimuli. These are our data. This is choice data, so number of choices made to each of our stimuli with mean proportion of choices to each stimulus on the vertical axis. Our control bees, so those bees that did not get any unexpected reward, are in dark brown, and our experimental bees that got that boost of sugar water reward are in light brown. And we did see a difference between our groups at the ambiguous stimuli. Those are represented right here. You can see that our experimental groups are making more choices to our ambiguous stimuli than our control bees. This is great. This shows that they are in an optimistic mindset and they are demonstrating our cognitive bias. The other interesting thing we found, though, if we look at our control data, is our bees are actually making their highest rate of response to a novel stimulus and not to our trained S plus stimulus. Now, if you are familiar with animal learning, you won't be surprised at this. This is very standard peak shift that happens in discrimination training. So we actually could have expected this pattern of response from our bees. But if we compare it to our experimental bees, we don't actually see that shift in the same way. These are latency data, so the time that it took bees to go to the particular stimuli. Again, we're getting a difference between our control and experimental bees at ambiguous stimuli, where the control bees are taking longer to approach these ambiguous stimuli than experimental bees, because the experimental bees are more likely to be interpreting them as an S plus and getting a reward. So this is, again, that optimistic bias. But what we're interested in is this difference between our S plus stimuli and our novel stimuli. And what we can see in these latency data, similarly to in our choice data, our controls have shifted their response, so they are fastest to respond to novel stimuli that are close to the S plus over the S plus stimulus. When we look at our experimental data, we do not see that effect. So here, there is no shift. Now, as I said, this shift in discrimination training is quite standard. When you train an animal in an S plus, S minus discrimination, their response to the S minus shifts their generalization curve to the left away from that S minus and shifts the peak away from the S plus. But in our positive manipulation group, we did not get that effect. So our manipulation wiped out this standard peak shift effect. So what can we conclude from that? Well, the first thing we can conclude is that while everyone focuses on the ambiguous part of that generalization curve in cognitive bias tasks, there are things happening on the other side of that generalization curve, and people should be looking at that too. The other thing we found is that it seems that what drives the difference between our two groups in a cognitive bias task is the impact of this S minus on our control group, shifting that control group in a standard peak shift phenomenon. And this gives us more insight into the mechanisms behind cognitive bias.